Have fun, Niklas.
Okay. So yeah, welcome to my Zurich HaskellerZ talk about this little tool and library that I wrote recently, which is called hatrace, a Syscall tracing library in Haskell. So for those of you that come to the meetup sometimes and talk with me over the pizza, you know that I run into all kinds of really nasty problems all the time. So really, like everything I touch, it breaks. So when stuff breaks, it's very important that you can actually figure out what is going on and fix it, because for most people they can say, okay, I'm going to get by just keeping it this way, but for me everything breaks, so if I don't fix it, nothing works, so I cannot do any work, which is very annoying. So this means that I use certain tools a lot to figure out all kinds of problems with all the various programs that I use. And this tool in particular is something that I wanted to write for the last 3 or 4 years basically, and then as part of some work of FP Complete, some clients of us needed some very difficult problems investigated. So we're talking about the kind of stuff where you have some form of production problem that is very difficult to reproduce, and if you want to investigate that kind of stuff, takes 2 to 3 weeks approximately. So if you have very good tools with which you can exactly insert this specific fault to reproduce it and then eventually fix it, that's very useful. So some of that work has been funded by that tool. So here's our new agenda. So first I'm going to give a little bit of background knowledge. Most people will probably already know this. How do system calls work on Linux and what do they do? And also how to use the Hstrace tool, which is the system call tracer default tool on Linux, which is very useful and I use it all the time. Then I'll motivate a little bit why Hstrace and its usage should be scriptable, so that you can write more sophisticated analysis and do more sophisticated tracing of your problems. I'll give a tour through hatrace, which is both an executable that you can use like Hstrace, and also a Haskell library that you can use to use the full power of everything that you want to inspect essentially. And I'll also show how I've implemented parts of it and some contributions that I have already received. Then going forward, I need lots of help from you, people and others on the internet ideally, to make it more complete. There is some work in there that's of a number of syscalls available on Linux, which means that that's something that can be very nicely sharded automatically. People have implemented some of the syscalls, but many others need some help. And then I'll also bring across a little bit of my own philosophy when it comes to investigating stuff and working with system calls. Alright, so let's talk about system calls first. Pretty much all the time when your program actually wants to interact with the real world, it needs to do system calls to do I/O. There are these system calls are functions essentially that you can call that the kernel provides, and these functions have a specific API. In this case it is a C API, but you cannot just call them as C-style functions. They will look like C-style functions because the C standard libraries that you can use, for example glibc or musclelibc or BSD's libc and so on, they provide C-style wrappers across those system calls, but internally really the way it works is that you basically say, okay, which system call you want to do, for example here read or write and so on, and you put this into one register, for example on x86-64, it's platform dependent. On x86-64 you put the corresponding number of that syscall into one register, and then you put the file descriptor, which is the first argument for read, for example, into another register, and is pointing the third registers and so on, and then you invoke the system call instruction, and then basically the processor invokes the kernel, and for example on older architectures by triggering an interrupt, and then the kernel sees, okay, what is in my register, so now I execute on behalf of the user this request to perform some certain action inside the kernel. For example, writing stuff to a file on the file system, sending something over the network, and so on and so forth. So this is what the system calls look like. You can read about every syscall using the manual page section 2 essentially. So man to write, for example, would tell you what is the API of this write syscall, and it would describe what that kind of stuff looks like. So for example, you could say man to write And then you would see here, okay, this is the C API, and these are the conditions, what this system call does and how you have to prepare the arguments and so on. And also it tells you what kind of errors you can have. So you have a return value, for example, for this syscall, -1 if it fails, and then it sets the error global variable, and then you can see here these various errors that can happen. For example, your disk is full, or the file does not exist, and all this kind of stuff. So that is system calls. Okay, so how are these system calls made in a very low-level fashion? In assembly, so we write the simplest syscall that does hello world and then exits with exit code 0. How does this work? So this is this example that I found on the internet. It's very common, but I found that this person wrote it down in this very nicely formatted way. So you basically say, okay, my elf executable starts at this section, and then we do 2 syscalls, this and this one. This one is a write, this one is an exit. So how does this work? We say, well, we use system call number 1, which is the number for write. Then we move this into the register A. Into register D goes the first argument, which is the number for the standard out file descriptor, which is 1 in this case. Then we put a pointer to the message that we want to write, in this case the string hello world, which we have declared down here. So we put its address into the RSI register, and then we put the length of how long this buffer is, how much of that the kernel should print, into the register D essentially. And then we invoke the syscall instruction, and then the kernel will do that for us. Afterwards, so technically the syscall can also fail, which we haven't handled here in this assembly. So for example, if you provide some garbage file descriptor in here, then it might fail, and it will give you as the return value, usually then also overwriting this syscall, this register RAX with some information that says, okay, did this fail? Then it's usually some large number in this case. If it succeeded, it will tell you how many bytes it has written. Because if you write to the network, for example, you may only, if you provide like a 1 megabyte buffer, maybe it only wrote like the first 10 kilobytes or something like this. So usually it returns that. In this case, we ignore it here. And then for exit, same thing. Into register A, we move number 60, which is exit success, and which is exit. The exit syscall, and then exit success. This code is exit code 0, and then we syscall that. How do you compile something like this in assembly? You just write the file down, then you compile it, for example, with a NASM assembler in this case. You link the object file to an executable, you run it, and it does hello world. And this program does really only those 2 things and nothing else. I show you this for a couple of reasons. One is Hstrace's test suite, to which you will obviously all contribute, sometimes needs some assembly in order to write specific system calls, so we can see whether Hstrace can trace them correctly. We do this in many cases instead of writing stuff in C, because in C, the C library can still add some wrappers or use some different system calls. So for example, instead of opening a file, it might use open@, which then you cannot test anymore, depending on which libc is in use. So in this case, writing assembly directly can be very useful. The second thing is also because this positioning of values in registers is also how hatrace and other tracers, Hstrace for example in GDB, how they can actually see what syscalls are going on. I will show this a little bit later in detail, but the way that this works is that there is one system call called ptrace, which tracers use, that if you tell the kernel with ptrace, please stop at the next system call, what it does is that it will, when some program that you trace does the syscall, it will send a stop signal, so this means the program will stop, and then it will allow you to query the entire state of the program currently running in this stopped state. So this means you can then look at register RAX, you see there is a 1 there, so then you know, aha, that thing must be in the right syscall. You can look at the other registers, you can look into the memory of the program, and that way you can read out that string. And this is how Hstrace shows what the actual contents are that are passed to a write syscall, for example. I will also give a short demo of that in a moment. So this positioning of these registers is very important, because that is what is essentially implemented in the code, peeking this information out. Okay, so let's do a little Hstrace demo in this case. I'll do this live in that case. People who can only see the slides, they can look at that. But here we have some live example. So for example, let's do here this example of Hstrace. First, this Hello World program I showed before, I have compiled it in this case as example programs build and then Hello Linux x86-64 in this case. So let me first run it out. So there we go, this is just Hello World, right? And then I can write Hstrace in front and it will show me all the system calls going on. So what can we see here? We see first an execve call, which means that this program is started. It shows me what the arguments are here, abbreviated. I can make this longer by passing a flag to Hstrace, so I see everything here. There are also some environment variables involved which are hidden. Then I can see the write syscall, and then I see here some interleaved output, which is the actual writing of the hello world to standard out, while Hstrace itself writes to standard error. So for example, if I hide this, the actual output, if I hide this, then we can see, okay, this is the actual Hstrace output, and this is the interleaved hello world that's happening. So we can see here, write to file descriptor 1 with this string of length 14. It returned that it did write 14 bytes, and then we can exit with 0. So that's what a very simple assembly program looks like. We could also trace something else. For example, let's say bin echo hello world. And then we can see, that is already much more complicated, because here we see the effect of dynamic linking. So for my program before, if I check here with LDD, I can see that this is not a dynamic executable, but a statically linked one, while bin echo is a dynamically linked executable. So it depends, for example, on the C library and some other stuff that is relevant for implementing tracers, but not for demonstrating this here. So when we have a dynamically linked program, we will see, for example, first accessing some files relevant to caching dynamically linked object files, and then eventually we will see that somewhere here it will open the libc, which is this thing here, standard library file. It will load it, it will map it into its memory space, so that's where we see these mmaps down here, some other syscalls. We'll close the file eventually, so now it can use all the printf and these other C functions that you usually want to use. There's some other stuff going on. For example, it opens the locale archive so that printf can print stuff depending on your current locale settings and so on. And then eventually your program will actually run. It will do the one syscall that you wrote there, which is also just, let's say, printf or what, and then call close and then exit in this case. So this is how Hstrace is to be used. Hstrace has lots of useful flags. So for example, if you have a program that spawns other programs, you can pass a -f, and then it will trace into all the sub-programs as well, the children of the child that you are spawning. You can also pass a -e, and for example say, I want to see only open syscalls, and then you can see only those. So there is already some functionality for like filtering in Hstrace in there, but we can see later how we can make this kind of stuff much more sophisticated. That was the Hstrace demo. So system calls are great because they bring transparency into our computers, essentially. Usually we don't know what the hell is going on, specifically with, well, of course also with our own programs, but even less so with closed source garbage from the internet that you just run on your computer, right? What does it do? You don't know, because there's just some assembly or like, I don't know, some interpreted, minified JavaScript, this kind of stuff that you run to run your chat applications. But with this system call boundary, every program has to go through it, and this is kind of open to you for inspection. So this means even a closed source program usually needs to make system calls to write something to the terminal or to the screen or to the internet, this kind of stuff. Of course, there are some limits to that. So for example, if you have a closed source program that talks to, I don't know, over SSL with some other servers, right? Then on the system call levels, in the same way as in a Wireshark or TCP dump or so, you will see just encrypted garbage. But for most things that is done to your own computer, you will exactly be able to see what that thing is doing. And this works for any programming language, right? Not specific to Haskell. You can take any program, run Hstrace on it, and you will immediately get a very good idea what that thing is doing and whether it's doing something stupid. So this means I actually use Hstrace every day for every problem. So if a program doesn't do what I want, I first run Hstrace and see roughly what is it doing on the highest, well, technically you could say lowest level, but on the highest level when it comes to doing something to my computer. So super useful. So you can then immediately see, for example, bugs. Does it open a file that doesn't exist? If it just says error, did not succeed, and you're like, well, what did not succeed, right? Then you can run Hstrace and you will see the, let's say, an open Syscall where it says at the end, no such file or directory. And you're like, oh, okay, it opened this file and that didn't exist, and the programmers didn't make an effort to propagate this information to me. But with system calls, I can see all of that, no matter what the programmers thought they have to do. And you can also spot performance problems, which I find all the time at work. So for example, a common thing in data science is running stuff, let's say in Python, and opening the same CSV file for everything that you're processing again and again, reading like gigabytes and gigabytes of stuff when you can read it once. Hstrace will immediately reveal this because it will scroll by with like tons and tons of output, and you can see, well, that is the same output all the time. Maybe that is not necessary. You can also see when stuff hangs, when stuff is unusually slow, what exactly it is doing, because there are only two modes in which a program can really be when it's running. One is it is executing CPU-intensive stuff in user space, and the second thing is it is blocked in a syscall asking the kernel to do something. There are only these two modes, either high CPU or waiting for something in syscalls. There's nothing else. So this covers this one part. So you can see, for example, if it's doing lots of network I/O, if it's waiting for another site and so on, that is what you can use Hstrace for. And I've used that for everything. So for example, I also found a bug in GlusterFS, which is a distributed file systems, which has an index somewhere, and they used SQLite. And this was incredibly slow. Like this one operation with just a couple of files, I had like only like 1 million files in one directory, so not a lot. And it was just like taking forever. And I found that using Hstrace, it was opening an SQLite database, and it was doing repeated queries to this SQLite database. And you could see that on every query, it would read the entire contents of this 20 megabytes SQLite database, which is not usually something that you expect from a database, right? You expect it to do a very quick index lookup somehow. And that way you could, or in this case, I could immediately guess that they forgot to define an index in the SQLite. So this means that it was doing a linear scan as opposed to an indexed, let's say, B-tree lookup, for example. So this means from this incredibly low-level stuff, you can immediately conclude certain misbehaviors of the application, and then you could go directly to, let's say, select something from or whatever, and then you can see, did they create an index or not? You see they didn't, you add it in, gets 2,000 times faster, and you're very happy. So this is why this kind of stuff is useful. But while Hstrace is good for inspecting what is going on, that's something, it's still a manual task, right? The programmer starts Hstrace, there's tons of outputs, adds some filters and so on, and in the end, then you can maybe figure out what is going in this specific case, but sometimes you want to do stuff that needs to be automated, right? Sometimes you want to say, I want to find exactly whether the program is doing a certain syscall, because, for example, I think that is bad, should not be doing it, right? You may want to implement some test suites where you say, I expect that this part of code only does the following syscalls, or I expect that it, for example, writes large buffers as opposed to, for example, puts stringline in Haskell, which puts one character at a time to the terminal, which is incredibly slow. So you want to assert something against this automatically. You may also want to say, okay, I need to do interaction with this program at a certain point. So after it does a specific syscall, I want it to stop, I want to mess with it somehow, or I want to change the situation, and then I want it to resume and see what happens, right? So that is something that Hstrace also can not really do. By now there are some basic scripting functionalities in Hstrace, but it's not something that, for this you want an API, right? You want to program that kind of stuff. You write a purpose-specific program that does just that thing, and you run it, and it always gives you the same reliable results without manual inspection and so on. So we want an API for that. So this is what I made hatrace for. There are two parts of it. There is the hatrace executable, which is supposed to be some kind of like fancy Hstrace, like alternative or replacement that you can use in certain situations. So I have this grand plan to get like half of the internet using it by adding colored output. Everybody knows this is how you get users. Also JSON output, this is how you get the other 50% of users, right? So this way, this means, for example, if I put everything in JSON output and allow some basic communication, this means you can use it from any programming language, don't need to learn Haskell for that, which might be some kind of limitation, right? Of course, it has some drawbacks also compared to Hstrace. Hstrace is ultra portable. It has support for tons and tons of architectures. Again, these like syscalls are dependent per architecture. So, for example, which registers to put stuff in, the numbers of the syscalls, and so on. They are all dependent on the architecture. Actually, I'm going to show a quick thing for that. So, if you want to look up what a certain syscall is, you can, for example, go to this website, which has a nice table. So we can search for, let's say, open here, and then we can see, okay, then on x86, or i686, or i386, this is like what open, like for example, open and open at, have these syscall numbers, and these are the registers involved, and you can click here to go directly to the kernel source code and see where that kind of stuff is handled. This is for one architecture, but there is another page which is not just pretty, but more complete, which shows you for each system calls, for each architecture, I'm just scrolling to the right here, for each architecture, what each system call number is, and whether it's available. Some don't exist on some architectures, for example. So here, for example, we have x86-64, which is my machine, and you can see that, for example, already between 32-bit and 64-bit Linux, the syscall numbers are different, right? Here, for example, like X's 33 versus 21. So all of this work has been done in Hstrace, but for hatrace we have for now only this one and this one. But of course you can add more. And of course you're limited to the architectures that Haskell actually runs on, or GHC can compile to, right? Okay, so this is executable, and then we have the Haskell library, which gives you the full control over everything. So every little thing, or close to every little thing that you can do with a ptrace system call, you can do with the hatrace Haskell library, with a very nice typed API that is like super clear on what data comes from where and what exactly it does and so on. I personally find it a lot easier to modify this than to modify, for example, the Hstrace executable, which might also be a choice, right? You just modify that. But it being a library, you can write programs on top of it that will continue to work in the future, for example. And yeah, it makes writing custom tools and reproductions for bugs very easy. Okay, some use cases. So what can you do with hatrace? I will just go through a longish list. You can also find it on the README of the project of what you can do. So most basic stuff. You can get all syscalls into a list and process them, right? Did this thing to that syscall. You can use it in general to audit high assurance software systems, which is what I do at work. So for example, you can see, does this thing write into a certain path? Does this thing use like fsync to ensure that when you turn off the machine that everything is written to disk, right? If it doesn't do this, like does it do some network calls that show that against the specification the program does not acknowledge the write only after it has persistently written it to disk, right? So might it use your money, for example? That's one thing that you can inspect with tooling like that. You can debug difficult bugs that can only occur in certain rare situations. So this means you can say, well, run this thing forever, but only when this one specific thing happens. Let's say only when the microsecond is like divisible by 3 or something like this. Then stop the program, then something bad happens. You can change the results of system calls because you can do whatever you want to the process. This means that you can create situations that cannot usually or should not usually exist in the real world. So for example, you can say what happens if Google.com, right, does not result in some if you dig that or like do a DNS request, it does not result in a usual IP address, but what if it results to localhost, right, 127.0.0.1, for example. Most of the cases, the programs will not be tested against that, but with this kind of interception, you can say, well, what if, right? You can just make it do it so, and this means also you do not need to modify the program for this. This works with closed source software, right? You can also say, what happens if a syscall, if a write syscall somewhere in my database application returns that the disk is full. This is rather difficult to test in many cases because if the disk is full, perhaps your program won't even launch, right? But you may want to test what happens exactly when the disk is full, when the critical write operation is done. This you can inject into your program using this approach. So I found another bug, for example, in a tool called Stolon, which is a high availability wrapper for Postgres. It's a Go program, and in that Go program you basically have 3 or 5 Postgres instances, and Stolon rewrites the config file of Postgres for you so that you can have automatic failover when one database fails. Usually Postgres is designed for doing this automatically, but with Stolon you can say, well, detect automatically or in the background using distributed consensus, detect when one of them is down and then rewrite the config file so that the other one takes over. And in this program I found one critical bug essentially, which was that the return code of the write syscall was not checked for success. So it would say, okay, I have written this new database instance is the master, but that would fail internally with the disk is full. But because Go does not force you to handle return values in all cases, it does for many, but not in all, the programmer did not check whether it actually succeeded. So that meant, of course, 24 hours of downtime in production. So, and this kind of stuff, you can simulate those problems using Syscall, rewriting, changing the results. Okay, so that's basically what I just said, bug reproducers. Like this way you can show, okay, I've encountered such a case, I want to show every time that it happens. So for example, you can say, I want to kill my build tool at a third system call that writes to a .object file, and see whether it will be able to recover in the next one. So you can already guess that I'm talking about the Glasgow Haskell compiler in this case. On the stack issue tracker, we had numerous reports where people said, sometimes when I build and then I press Ctrl+C and then I do stack build again, then it just throws me some linker error. And the only way to fix it is if I do stack clean and wipe the build directory out entirely. And they were like, okay, well, maybe it's a bug in GHC, not sure, and so on. And at some point, I had enough of that, and I said, okay, we need to investigate that. And with hatrace, I could investigate it in detail. And we saying, okay, what happens if I kill GHC in the middle of writing to an object file? Will it rewrite it? Or will it say, the file is already there, I don't have to write it again, link it in, but it's only like half of the file, so many symbols will not be found, so it will fail. And that happens to be the case, and later you can also see how then I made the reproduction for that. I will show it in the live demo, and of course I also wrote the fix for it upstream. Okay, what other things can you do? You can write test suites that assert that your code uses only certain system faults for correctness or performance. The thing I mentioned before, writing, for example, if you say, I don't know, I use the byte string library and I write stuff to a file, does it do one syscall per character or does it do a 10 megabyte write? Similar thing with HaskellerZ that I mentioned before. I found some bugs where I saw that when it does network round trips, it does multiple sends, like packaging stuff into lots of overhead in various network packets instead of buffering them together. You can assert for that. You can mock syscalls to see how they would behave in certain situations, right? If you say, okay, I already imagine that this is what can happen, right? That this can fail. Let's do it as part of my test suite of my program when I'm developing it. So in this case, it's not even like investigation, it's preparation. For example, SQLite has this very extensive test suite where they basically say, okay, we have some tasks that SQLite should do, and they run it again and again from the beginning, killing it after each system call. So killing it after the first one, killing it after the second one, after the third one, and so on. And in the end, if every time they run SQLite again and they see it can recover, they can say, we have exhaustively tested like the failure of every possible thing that this thing can do like in the real world, right? So that's something that you can do to your programs as well. You can use it for fuzzing. For example, you can say, well, what happens if I insert some garbage data into this program, right? Do I get a seg fault? Do I get a security vulnerability? You can do this from outside. And you can also improve, like do smart fuzzing, right? Where you say, okay, I fuzz and I don't send only garbage data to the program, but I inform it by something that I observe the program does. So for example, if I see that it talks a lot to a certain internet domain, right, then maybe my request, I could make them come from that domain. So I can really like inspect and modify everything. And you can also use it to add features to existing programs that were never designed to do that kind of stuff. So for example, there is one interesting paper and also a couple of implementations that basically say I wrap my programs using Hstrace. I wrap them such that when they try to open something @ magic internet, right, that then instead of failing that this path doesn't exist, it downloads something magic from the internet, right, and returns it back to the program. It says, here's the thing. So then you would type like ls or like my wrapper ls/magic internet something, and files would magically appear there, right? So you can do that kind of stuff. Or you could add logging facilities to programs where the programmer did not add any logging there. You could say every time this thing writes to a file, also put it into this log file in JSON format. That kind of stuff you can do. Okay, so now we go for some examples. Inside the test suite of Hstrace, I show some of those things. Of course, this is just like a very small subset of what can be done, but let's look at that. So here we have inside, so I should first say, of course, you can find it here, GitHub image to Hstrace, and the test suite can be found in test, surprise, and the use cases are also calculated here. Okay, so I'm just gonna go through this a little bit. So the simplest example here is that I say, okay, I trace a forked process. So my program starts this other program and also traces it, and I say this should succeed. Okay, all right. And in general, it should not crash. Very boring. But let's now look at the actual, like some actual use cases. So there's this function which has a very German name, which is source trace for exactly full path with sync. And as you can see, this takes as arguments an argv array, essentially a list of the program and its arguments, and it accepts as another argument a conduit, so like a streaming processor, that says what to do with each event that occurs, each tracing event. So it will tell you always which process ID will raise this event and what the event is. And then these events might be, I entered a write syscall, or I exited a write syscall, or a signal was sent to me, or I died, and this kind of stuff. So this is what this thing does, and then we can write some streaming processors over these events that come streamed in. So I show some examples right here. Like the simplest one is that we say, okay, I don't do anything with it, just return unit and it succeeds, okay. And then we have here, it allows us to obtain all syscalls as a list for this Hello World assembly program. So in this case, what I say is that, well, first I compile it, and then I resolve the relative path to an absolute path, creating this argv buffer, and then I say source trace for exactly full path with sync, argv, and then CL consume to just gather the stuff in the list. I want to do no interactive interaction with that thing here. So this gives me these events, and then I filter this list of events saying, okay, please ignore the PID, give me all the syscall stops. There are also other things like signal stops, death, and so on, where I enter a syscall, and that syscall, please put it into the list. And then I can say where the program exits success, and it returns me 3 known syscalls that I know by this sum type here, namely 1 exit VE, 1 write, and 1 exit. And then I can see, is this all the program does? Yes, then the test suite will succeed. It also can show, for example, that if you try to run a program that tries to write to a bad file descriptor, that then instead you will get an error with error number like ebadf, for example, in that case. So this thing always returns, in this case, an either essentially that says, does this thing succeed or does each syscall fail? And we look at this in a moment. What other things can you do? Like sub-process tracing, like strace -f. We can say, okay, I want to run bash as the program, and bash inside runs first this program and then and true. So then like this program is a child of bash, which is a child of me. And in this case, I want to see, okay, filter me all the syscalls where the syscall is one of clone, or which is like something to spawn new threads and processes, and write. And then I can say, yes, indeed, I have these 2 syscalls observed and nothing more than that. Also a couple of open tasks in here that I still want to implement. And I'm going to also quickly show here the API that Hstrace provides. So for example, just scroll down a little bit here. Okay. So you have for each syscall First, there are these 250 something syscalls in there. Of course, I have them auto-generated with a template Haskell somewhere over there. I can show that in a moment. But that gives you essentially here this syscall rename, syscall write, and so on. Those are auto-generated. There are known syscalls for those that were present at the time I compiled it, and unknown ones where I said, okay, if I observe at runtime a new one that I didn't know existed, then I just return the integer that is there in there under a different constructor. Then each syscall can have different data based on whether we are entering the syscall or exiting the syscall. So for example, main to read, in the read syscall you provide a buffer into which the kernel should write the data, and then the kernel will fill it in. So this means in the beginning you usually provide like a buffer with nothing important in there, garbage or zeros or something. So this means that at the enter time of the syscall there will be garbage, and at the exit time there will be the values that you want. There may also be some syscalls where you provide something that is not garbage and the kernel changes it. So this means we must be able to inspect the state of the program at enter and exit of each syscall. This is why we have different details for each syscall for enter and exit. So for example, the open syscall here, man to open, we give it, in this case, we give it the path name to open, the open flags, and the mode, and it returns the file descriptor or an error. So in this case, for open, we give the path name, the flags, the mode, with its corresponding C types, and some Haskell convenience, for example, the path name as a byte string, which you can work with more conveniently than with this pointer to chars. And then for the exit details, we always retain the enter details, because sometimes you want to write filters and so on that need to look at both the state before and afterwards, and here the FD that was returned. Okay, and we have this for each syscall, and that's something which I need some help with for syscalls that I have not implemented yet. Scrolling down a little bit across various syscalls, right? So here we have a sum type that has which are all the detailed enter and exit syscalls that I can have with the respective details here, and some functions to get the data out. And then I also have this thing that I wanted to show one moment. Here we go. What are these trace events that I showed here, that this long function with a long name, what can that emit? It can emit that the program died, that it did a syscall, either start or stop, so entering or exiting. That it entered or exited. It can emit special events, for example, a new child process appeared. It can say the entire group stopped, or a signal was delivered to this thing. And then, so the stop types, then either enter and exit with the syscall, and the args. The args in this case is just a set of registers, and then you can call this helper function that translates these args, which is just a couple numbers usually, so just a couple registers, right, into their corresponding meaning, for example, peeking out the actual strings from the running program, and that gives you these detailed enter and exit parts. Okay, so this is the API. So with this knowledge now, we can show some more interesting examples. So, for example, here we have for program inspection, we can point out that the difference in syscalls between atomic and non-atomic writes is a rename. So I have this little file in C that I wrote here that basically writes usage, right? It writes, you can say either atomically or non-atomically, n many bytes into some file that you can provide. So how does this work? If it's non-atomic, it just opens the file here, does some error handling, and then writes, calls write until all the data has been written to the file, doing the various C error handling that you usually have to do on the low level. And then if you pass atomic, it will first write it to another file and then do rename here, so move in the terminal, right? Rename it to the final location. Why do you do that? You do that so that if in the middle of doing your write syscalls, you turn on the computer, you turn it back on again, and you have a file where only half of the contents is written. That's the kind of stuff I mentioned before that we observed there in GHC. So the solution to that is you write it to some temp file and then move it over. And it's important that this file resides in the same file system, because only that guarantees atomicity of this move. Otherwise, this syscall rename will actually fail, and the move command will just copy it over and again do a write loop. So this is this writing stuff atomically, so we can run it here in example programs and then atomic write, and then we can say non-atomic 10 bytes to test file, and it says, okay, writing those, so I can cat test file, and I see this, and I can also say atomic, and the same thing happens, but I did it atomically in this case, so let's do strace on this. So non-atomic strace like that, and here we can see indeed it did a couple of writes. I did an open, did a couple of writes, and then it did a close, and then it did an exit. While if I say atomic, then I can see it's writing to test file TMP instead, and at the end doing a close, and then doing a rename. So now I want to say, so this is where I can inspect this kind of stuff with strace, but now I want to programmatically say I want to diff the syscalls of that guy and the syscalls of that guy, and I want to say the exact difference between those two is a rename. So that's what I do here in Haskell now. So I say, okay, so this difference is a rename, so I say, I make myself this helper function where I can say, give me the syscall set for, I give it the program to run. Actually, I just give it the arguments. It's always the atomic write programs in this case. And then it says, it gives me a set of syscalls that this program did. How does this work? I call my favorite function, source trace fork exactly full path with sync, turn it into a list, filter all the events that are syscall enters, assert that the program actually succeeded, and then return this as a set. And then I say, okay, I want to write 100 bytes, and I want to do it once for the atomic argument and once for the non-atomic argument, the remaining arguments being the same. So this gives me two sets. And I say, well, complete me the set difference, which is this difference in syscalls, and I say the difference in syscalls should be the singleton set with the renamed syscall inside. And then this test will go green, if this is the case. So this way I have automated this. Then, two more examples. We can do program misbehavior detection. So the first thing is that if I send a sig term at just the right time to this atomic write program, then if I use the non-atomic mode of writing, this can leave me with some partially written file. But if I use the atomic writing mode, and I send a sig term somewhere in the middle of those syscalls, then it will not result in some partially written files. So how does that work? So I make myself here this helper function, kill after 3 writes. So what does that do? Again, it calls atomic write, it starts tracing it. I have a helper function isWrite that returns true. If we're an enter syscall to like an enter event to a write syscall, and then I say I use my favorite function with this thing kill at the 4th. So after 3, kill at the 4th write system call that has been made, kill it. So this is a conduit here consuming the events. I first conduit filter away all of those that are not writes. So then I have only the writes. And then using the HaskellerZ of very like familiar way of doing streaming programming, I can very conveniently write these pipes where I say, drop me, so pipe this into something that first drops the first 3 and then kills the program, where the kill conduit just says, well, wait for the next event and then send a signal to the child pit with subterm inside. So this means I will kill this program after the 3rd write. And then I can say, well, so this was my helper function, kill after 3 writes. So what do I do now? So first, I run the thing with kill after 3 writes with non-atomic, then I read the file contents, and then I check that it either has 3 A's or 4 A's inside. So not, and we can see it's not atomically written, it has not written the entire 10 A's. And then I remove the file and I do the same thing with the atomic fashion. And then if I do this, I just assert when the target file should not exist because it's writing it to the temporary file. That one got cut off, but my target file is either there in its entirety or not at all. And this tests 2 passes. And then finally, we have here the example that it can be used to check whether GHC writes truncated object files or executables. So this is a little bit more sophisticated, but still relatively easy here. So we say we want to write this, the target file is this Haskell hello world. This one is just like hello.hs, just a simple program here. We want to compile it with GHC. Now, I can either compile it with that GHC here, or this GHC on my computer where I have implemented the fix, and which I have pull requested upstream already. Then I provide the arguments, which is ghc:-make. I say where the output should go, what the input file is, and what the name of the executable is. Then I check so that this test also passes in the future when upstream GHC has fixed it. I also do a check on the GHC version, and if it's smaller or equals to GHC 8.6, then it say, okay, that says the test should fail, but for 8.8, where my patch is in, it should not fail anymore. So that's just some version checking, essentially. Okay. So here is the helper function. Do a full ghc:-make build with the killing. So I do force recompilation so that it doesn't cache build outputs. And then what do? I write this conduit here, and the purpose of this conduit is to say I want to filter everything away that is not writes to .o, so object files, right? So I say, okay, ignore it when it's anything but an exiting write syscall to a file descriptor. I look up the name of that file on the disk in /proc, which is where Linux stores this mapping from file descriptor number to path. So I read this, it's a symlink in there. So for example, you can just do like proc self fd, and you can see these are all the open file descriptors. This is where they're pointing to. For example, standard out to my terminal here for my shell. And then I say something is a relevant file if it has example programs built somewhere in the path, and main.o, which is the thing that I'm writing. Of course, you could also say any object file, right? But in this case, I just say main.o because that's the file that I'm interested in. And then I print something when that happens, so some interactivity, and then I yield it on so downstream parts of the pipeline can process it. Okay, I have my kill conduit as before. So now I run. So strace for exit full path with sync. I take a helper function that gives me already filters away everything that's not the syscall exit details. Then my filter conduit up here that gives me only those that I'm interested in. I take 3 of them, and after the third one, I kill it. And then I say, okay, then the exit code should not be success, right? It should fail. If I kill it, it should fail. And this is my helper function, run ghc:-make with kill. So what do I do now, right? So then now the idea is I'm going to run GHC, I'm going to kill it this way, and then I run GHC again, and the expectation is that GHC will pick up anything that it has done before, and if there is some corrupt, like if the file is like corrupt, if last time it was interrupted, for example with Ctrl+C, it will finish the compilation anyway. It will just rebuild any files that are incomplete. So what I will do now is that I will do this, and I will assert that if it's a broken GHC, then it should fail that next time with a linker error, which is what current GHC does. And if it's a patched GHC, then this should succeed. So what do I do? First, I clean up all the files that GHC usually produces. And I first called build normally, and I record how large is the output, the expected output file, essentially. Right? And then I say, okay, now I build it from scratch with a kill. So I run this, and I expect that GHC then prints, okay, linker error, whatever, truncated file, that's good. And then after this, I do, I run, so if it's working, right, in this case, if it's not a bug GHC, then I call the normal GHC again, and then I check whether the created executable, or the created target file in this case, yeah, the created executable, has the same size after a build with kill and a rebuild as if I build without kill, right? So they produce the same output, which is this environment that GHC and Cabal and Stack and so on are usually supposed to provide. For any state of your build directory, you can run build and you will end up with the same build artifacts. And then I assert that these two should be the same.
So you're checking only the same size of the build artifacts?
Yeah.
Are the build artifacts still non-deterministic?
So
shouldn't they have the same hash?
I think in this case, if you build the way that I did here without like GHC-J for multiple jobs and so on, then I think this will actually be also byte by byte deterministic output for GHC in this situation. I think yes. But in general, for the purpose of this bug, I only want to see did it cut it off in the middle, right? That's why comparing the file sizes in this case is the same. I could also compile, actually remember the actual bytes and check were the same bytes generated. I could do this as well, but then I would test for even more determinism essentially, not only the does it cut off in the middle. And now we can do this. And by the way, this bug in GHC was extra bad because in most cases you would end up with build errors, right? It would give a linker error and fail. But if the file was cut off just at the right time, then the link would succeed, the linker would succeed, and you would end up with an executable whose assembly just ends somewhere in the middle. And then it would build successfully, you would deploy it, and it would crash at runtime. Very nice. Okay, and that's the kind of stuff that I wanted to show, essentially. And yeah, so after this, so this is essentially my repro. So in this case, it is a little bit longer. I mean, much of it is comments and detailed output and so on. But in this case, we have like 130 lines for this reproduction. And the alternative before, my colleague Alexei made something before when we investigated this bug that already showed the problem by just making a loop of stack build again and again and killing it at random times and seeing whether the error occurred. So this worked, and after running it for like a couple of hours, it would reveal the problem. But of course, as a repro to like show to GHC developers and say, look, this is a real problem, it's not so good, because if you tell them, oh, just run this thing for a couple of hours and hopefully it will happen on your computer, if you have a slow disk, if you have a fast disk, maybe not. So this way you can provide something that fails every time, right? It fails in a guaranteed fashion, and it is still relatively short. And you don't have to wait for a couple of hours either, so that makes this quite nice. So let me see if I can get here our new GHC GitLab and open this bug. It's a bit slow, but I'll just keep it loading and hope that it eventually comes back. Okay, so this was that. Let me just scroll a little bit more. Ah, yeah, right. And then further down, I also have per Syscall tests where I have a couple of mini example programs. For example, if I like run -c echo hello and I pipe it into cat, then I can observe that cat, for example, does a read from started in, or for execve, I can run a program and then see that execve was done, and so on. So for each Syscall, there are a couple of tests. In the same way, Hstrace also has that. They have a very large test suite where they test for every single Syscall, can Hstrace test it correctly? And one of their open to-dos would be to just steal Hstrace's test suite and just like auto-generate test cases based on their auto-generation so that I don't have to do it. This thing is also, this concept of reusing existing stuff is also here already. So for example, for getting the syscalls for the different architectures, I didn't want to maintain this table myself. I didn't want to grab it out of the kernel headers myself. Instead, I just have a submodule of somebody else's project here, a syscall table, and that I just parse with template Haskell, which has the syscalls, for example, for i386, and you see each name and its syscall number. So reusing code is good, but the GHC track doesn't load, so GitLab. Let's continue with this. So this is just what I showed before, right? It's one of the examples that I just showed. Okay, so how does this work? It is built on the ptrace system call, which is the thing that both Hstrace and GDB are built on, and now you can see why, right? Because it gives you the ability to read and write anything in this program. And then GDB, of course, has just a little bit of extra feature that can understand contents of memory as C structs, for example. So what kind of events do you get there, right? So you get these ptrace event stocks, as I mentioned before, special stocks for a program spawned, or a program like forked a new thread, for example, this kind of stuff. The syscall stocks, enter and exit, signal delivery stop. For example, if something gets a SIG term signal from somewhere else, you sit in the middle and you can say, oh no, I just don't tell the program that this signal came in. I just keep it to myself and let it run for a little bit longer. Let's see what happens, right? So that way you can test, does your program correctly terminate in certain situations when certain things happen or don't happen. And then death, of course. You can read and write memory and registers. So this way you can inspect everything, system calls and everything else as well. And then when you're done with inspecting, you can say, okay, program, now you can continue running. And you can do that in every thread of the program independently. So you can also do fault injection, for example, on one of the threads of the program failing and seeing how the rest of the program reacts to it. Okay. Some more tour through the implementation here. So in our Haskell, how does this work? Like, what are the main functions? Of course, the key thing is this guy, right, which gives you this conduit for streaming action. And here you can see the various options that it sets that perhaps I also make optional at some point. So if you look at the main page for main to ptrace, which is the tracing system call, right? So you can say, okay, do this for me, kernel, please. It's a very long page with lots of details, but I at least believe that the Haskell API makes this kind of stuff much easier, and you just get this really easy stream that you can then filter away. You can then, for example, say, okay, I want to subscribe to certain events. You can say, I want to skip over syscalls to trace a little bit faster. Right now, the program stops at every syscall, and then you can do something, and you can say resume. Sometimes, if you want to speed up something, so for example, GDB's breakpoints, right there you could say, well, stop only in certain situations. So this is basically what this thing is a wrapper around. And for example, peak data is this flag for ptrace where you can say, okay, give me data, give me this byte, or technically give me this word out of the trace's process memory. Okay, so here we set those various options, and then we have the loop inside here, which turns the whole thing into a conduit, and then we can see that in each of these event situations, what do we do in this case? So we can, for example, return like that, like a signal was occurring and so on. And of course, if the program dies, then we stop the conduit, we do not loop anymore, otherwise we just keep looping. There's lots of implementation detail here commented, because this ptrace API is not super straightforward. You have to like read a lot of man page to really know all the corner cases, but it is well documented, I have to say. So there aren't really too many open questions. Like if you read the man page, then you can usually understand, okay, this is what happens, and then of course sometimes you can look at what does Hstrace do, and usually if you get something wrong, then everything just hangs, and then you're like, oh well, what did I forget here now? Okay, so, but yeah, so I wanted to show a couple of things. So for example, there's this function, get syscall enter details. So you give it the syscall that you have already like received. So for example, I don't know, 1 for write or whatever. The syscall args, which is just the up to like 5 or 6 registers in this case, the pin, and then it fills in the details of the corresponding syscall. How does this work? So for example, let's say for the open syscall here again, so we get arg0 is the pointer to the path name, arg1 are the flags and integer, and arg2 is the mode. So then you say, okay, I do a bit of pointer casting essentially, and then I say peek null terminated bytes from the running process at this pointer, and this gives me that thing as a byte string. So there are a couple of helper functions with which you can peek entire byte strings, as opposed to like word-aligned words, which is very annoying. So this just does this peek multiple times for you, and that way you can then fill in these enter details and say, okay, I fill in this extra thing. And so for each function, or for each syscall, we have something like this. So for example, for like, I don't know, for write, we can read out with peek bytes here the buffer contents and put them in here. So if you want, which you do want of course, to add new syscalls to Hstrace, what you would do is you would create one entry in these some types of which syscalls exist and have details. You would create one entry for get syscall enter details, where you peek out the data in here. So most of the cases this will be peeking out some. So if it's a simple type, it's already there in the integers as registers, and you just need to cast. If it's something more sophisticated, it will usually be a string which you peek out, or in some other cases it might also be a struct, right? So for example, in this case, stat. Let's see, where's the basic stat here, right? Returns a struct, or fills in a struct stat, and a struct stat looks like this, right? So in this case, you may want to make a data type with, I don't know, a storable instance or something like this, and then fill this in, and Hstrace, for example, can print it nicely formatted and like what those things are. So that is filling in the enter details, and then we have the same thing as well for getting the Syscall exit details. So for example, in most cases, many of them don't add any new details, right? But for example, read is one of them that, let's see where read is here. So read, for example, in read we have to peak bytes when it returns, right? Because then new data is there, and then we can put that in. So in general, it's just, each Syscall is just a couple of lines. So if you feel like you have a free weekend, maybe you can add a couple of them. And in general, of course, if the question is which one should I add, run your favorite program under hatrace and see where it says Syscall not implemented. So then it will just say, we can maybe show this here as well. This is the hatrace executable, bin ls here, right? So okay, here we go. So this is the basic output that just has like lots of like show being called, and you can see here, for example, execve actually has the full details, which I have already implemented in some nice form where I say, okay, it's ls, this is the arguments, and these are all the environment variables afterwards. But you may also find some unimplemented Syscall. So for example, here we are entering a Syscall. We know it's mmap because that's auto-generated from its number, but the details are not implemented, right? So you can then here see only the registers, but somebody still has to translate these registers to an actual nice Haskell data type that says what's in there. And then open, for example, we just saw that before. This already has nice details, and then with the equals 3 also shows the return value, in this case, files the 3. So yeah, that is basically what I wanted to show. And one more thing at the bottom, how do I,
can you also change the Syscall exit details?
Yes, yeah, you can do that. In this case, I have not implemented that yet, but the way that this would work is that you say, you wait until the Syscall exit detail appears, right? And then you, let me just show it for, let's say, read.
You have to go modify the buffer.
You just write something to, you can just write something to the, well, either you can write something to the pointer, right, that was returned, assuming there is enough space, and just put this here, read, I'm sorry, details, read. So in this case, right, so there's this, the program already knows, okay, this pointer is being returned, namely here this, this buffer pointer, right, and you can read from it. So here you could poke some bytes into this address, and then it would see that, of course. And then there are, of course, other cases where you might say, well, there isn't enough space there, what I want to poke in there. For that, a little bit of extra functionality would have to be added, that you say, instead of overwriting that pointer, that pointer's like that address's contents, instead I change the register where it points to, and I allocate some big pointer somewhere else inside the user process. So for that, I still have to add like a couple Syscalls that allow me to do stuff like this, essentially.
Why would that work? Because isn't the target buffer allocated by the user program? And it will later on have assembly code reading exactly from that address.
That, of course, it depends on the Syscall, right? Some Syscalls fill in something. So in that case, if they fill in, for example, a pointer, then you can say where that pointer is that. If they already provide a buffer with a fixed length, so for example, with read, you say, I have this many bytes available, right? You say, I have this many bytes available. Then, of course, you need to stay within those bounds, right? So in most cases, this is actually the case where the user space program says, this is the memory available. Usually, the kernel doesn't really allocate stuff for you, right? I think.
How easy is it? So to do this safely, change, return a different read result. You also need the enter details for the read.
Yeah.
Does your API already do the correlation that and with exit details you also get the enter details?
The exit details always contain the enter details. So for example, so the exit details for open contains the enter detail, and the exit detail for open at contains the enter detail, the corresponding one.
Right.
So that you have them available always. I remember them. Of course, it costs a little bit of memory, but I just have them available here, and perhaps I make it optional in the future as well. And now, of course, what you can also change is, let's say, you can change the amount returned, right? If you do read, and you actually like read less, then you can say I just change this register that indicates how many bytes were returned. In that case, you have to change a register as opposed to like poke something into a buffer. Okay.
One last question on this.
Sure.
I mean, I don't know the ptrace interface, but could it be that you get an enter event and then a sig kill? So, or is it always such that enter and exit are just besides each other? How do you say? Can an enter and exit be sort of? Can there something be interspersed?
Can there be a kill in between? I think so. Yes. I think the kernel can kill programs technically while they're in the syscall. Actually, most of the time that will probably be the case, right? If you do, let's say, get line and the program hangs and you send it a sig kill, it will terminate, right? It will not wait for you to type something until it terminates. So yeah, that is possible. There are also, so I think signals can arrive at any time. Of course, there are also other special cases where if you get some signals while you're in the syscall may return with like an e-inter error, and then the program can decide what to do, right? But for a kill, of course, it's over.
Is kill the only one?
I mean, kill, I think, is the only one that immediately guarantees you to terminate the program. For the other ones, I mean, you can set up these signal handlers, right? To say I want to react to certain signals, and the default action when your program has not set up a signal handler for a certain thing is then to kill it. So I think the kernel tracks that as well, but I would have to look at the details for that. Yeah. Okay, and the last thing I wanted to show actually is how do I get here exactly this. So how does it work to get the entered detail, the entered syscall at all, right? So let's say I call ptrace on the thing, then it stops me. So how then do I know what's going on? In this case, so I actually will first show this up here. So here's this function, wait for trace event. What does this do? So we first call ptrace that says, okay, stop at the next something. And then we call waitPid, which is the standard thing that you also use to wait for a program to terminate or to like raise a signal or whatever. In this case, then it will go into stopped mode. So it will then say, okay, I'm now stopped. This PID is which one stop, because if you're tracing multiple programs, then any of them can stop, or multiple threads. And then we can see, okay, what is the exit status? If it's a stopped, then we may be in a thing where a syscall has happened. And then we can check various flags. So for example, if it's a sig trap, then all of these special ptrace events can occur, in which case then I create this constructor in here. And otherwise, if it's nothing here, then it must be a signal. And then there's this other thing, so that if this special thing is, if this special mask is set, then it is a syscall stop. So then I record this. And I also keep a map per PID that records whether a given thread is currently inside a syscall or not. And that is useful, for example, to trace, because ptrace doesn't currently tell you whether something exited or entered. You need to track that. The first time it calls you, it must be an enter. The next time it calls you, it must be an exit. So that way you have to always toggle in between those two. Unfortunately, it doesn't tell you itself. That's what this map is good for. And then, so how do we know? If it's a syscall, how do we know which one it is? So I'm going to show this here. So if it's a syscall, we call getEnteredSyscall on the PID. So what does this do? So we say, okay, let's look at the registers of this thing. And if it's x86, then we look at these registers. And if it's x86-64, then we look at these registers, which are 64-bit and different registers in this case, translated from this table that I showed you before. There's also some extra special casing, because there are actually multiple ways how you, so these couple lines are now what took like tens of hours essentially. So there's one extra trick, which is when you invoke a syscall, you usually do it with the syscall instruction that I showed before, right? Let me just go up here again. So syscall, that looks easy, right? But on 32-bit, the way that it worked is that you called int 80, so interrupt, you triggered interrupt vector 80 in the processor, a different instruction. But 64-bit is backwards compatible with 32-bit. You can run 32-bit programs on 64-bit Linux. So this means on 64-bit, both of these methods work. If you call or if you make the syscall with the old method, of course, then the program will also have used the old registers, not the one for 64-bit, but the one for 32-bit. So this means in order to determine which syscall it is, because as you remember from the table, the syscalls have different numbers. So for example, write has number 1 on 64-bit and has number 4 on 32 bits. This means you don't know which syscall it is unless you know with which assembly instruction the syscall was made. Htrace doesn't tell you which one it is. So how can you figure out? And the interesting thing is, Hstrace does not currently implement this correctly. So this means that if you Hstrace a 32-bit executable on 64-bit Linux, it will tell you completely garbage syscalls. The thing is not completely garbage because, like, for example, you do hello world, and then 4 is actually exit on the other one. So you will see that the first syscall it does is exit, and after exit it will do more, which makes no sense because after exit usually it's over. And you're like, what the hell is going on? But this is exactly the problem. So how do you figure out which of those two things was it? And there were recently a couple of presentations by some other people working on the kernel. They were pushing for extending the interface so that you can ask the kernel which of these modes actually is it. But there is another way, which is that, so how does this assembly stuff work when you do this thing, right? What happens technically on the stack? So you have these different, at the point where you return, right, your instruction pointer in the assembly, at the point where you return, it's here. So then you just go up 2 bytes and you see what is there. If it's a syscall instruction, you take the one code path. If it's the other one, then you take the other code path. Luckily, the interrupt 80 and syscall are exactly the same size, so it's relatively easy in this case to do this. So this means that here, so we peak. So the syscall location, so this warranted some comments, of course. The syscall location is the instruction pointer minus 2 bytes, so 2 bytes up. We peak the bytes, and then we just case on the opcode. If the opcode is the bytes for the one, then we say, okay, it's 32-bit mode, otherwise it's the other one. So that's that. So Hstrace, just gotta say that Hstrace has the code for that. And like I learned it from them there, basically. Actually, I learned it independently, and then I looked in Hstrace and it had the code, but it was just on a disabled code path because for some reason they didn't like it. I don't know why they didn't like it. But it had the code, but it wasn't disabled. So technically you could do it, but they chose not to do it. So the thing is that, the fun thing is that there is actually a third way that I didn't know about, and that I found out about because I investigate a completely different problem. So little tangent, okay? My mother has this Chromebook, which I gave her once because that was like a computer that we had available. So this Chromebook runs Chrome OS. Chrome OS cannot usually do the things that you want to do as a normal programmer. So I put some Ubuntu on it using some special method that like changes the kernel and so on. So that you can actually build a normal one. And then at some point, this Ubuntu there was very outdated, so I wanted to update it. So recently I updated it from Ubuntu 12.04 to Ubuntu 14.04, and then I wanted to update it to 16.04 and 18.04, just doing the standard couple years upgrades there. And then one of the upgrades failed, and that basically, because you cannot boot a live USB from there, required me to reinstall the thing from scratch, like flash the newest Chrome OS, well, newest, it's like end of life after 5 years, of course, plan obsolescence, but I had to flash the newer Chrome OS, and then I wanted to try a different method that did not require me to actually change this complicated stuff. Instead, there is a new thing called Crouton, which uses a CH root that can run an X server inside, but uses the Chrome OS kernel. So I did this, and then with Crouton you can choose. You want to install Ubuntu or Debugging or whatever, Gen 2 into this CH root. So then I ran this, I ran that thing basically, so I ran the Debian installer, and the Debian installer ran through up to the point where dpackage says configuring systemd. And then in this, in systemd, then basically an assertion was thrown, and that assertion made no sense whatsoever. And that I want to quickly show. So here you can find a rather longer issue if the internet actually works, otherwise I cannot show it. There we go. Okay, so let's not jump to the solution here, but somewhere inside systemd's random util, so systemd has to it generates some unique ID somewhere. For this it has to get some random data from the kernel. So then it calls getRandom, which is a syscall, and then it says, here's R, right? So if R is negative, it failed. If it's positive, then it did not fail. You can provide how many random bytes you want to have, n in this case. So if we got exactly, so if the returned bytes are exactly as many as we requested, that's great. We don't have to call it again. We got enough randomness. But there is this check that getRandom will never return more random bytes than you requested, which makes sense because you provide a buffer for it. So then it would buffer overflow, it says, essentially. And the systemd people were very clever in putting this assertion in here for something that clearly must be, right? There is no way this could possibly not be the case. And of course, this happened on my mother's Chromebook. So it triggered this assertion where it says getRandom returned more data than you asked for. So then, of course, I had two options, right? I could say, okay, well, whatever, we just buy a €150 ThinkPad of eBay, or we investigate this shit. So at that point, we put on our investigation light, and we started looking into what exactly is going on, right? So, and it turned out that here, what's happening is that the return number was, in this case, I think like 255 or something. I say this somewhere down there. It was the number, or the number that was returned is the number of the getRandom syscall. Okay. So when does this happen? Essentially, that happens when you put something. So rax is the number where at calling time you put in the system call number, and at return time it puts in the result. If the thing, let's assume syscall didn't do anything, then rax would stay unmodified. If software doesn't know that this is the case, then you would put getRandom, let's say 255 or whatever it was, in here. This won't do anything. Afterwards, the return value would show its own syscall number, and that was that. So it would return a larger number when it had only requested like 32 bytes or whatever. So this way, then I learned that there is a third way of making these on 32 bits only, of course. There is a third way, which is called sysenter, which was a syscall that was added because this interrupt 80 making an actual interrupt was too slow. But usually you make these, you write the assembly and make the syscall instructions in your assembly. But the problem was now, well, on 32-bit, there are these two methods now, right? But only processors newer than, I think, i586 would support this. So a very old one, i386, would not support it, but 586 and 686 would support it, all 32-bit x86, right? So this means you need to know which processor you're running on to decide which syscall to make. Of course, most user space software would not be expected to make this check at startup. So the kernel developers said, well, how about we provide this information, which syscall to make? So instead of making it such that the user application makes the syscall instruction for the application, for example, generated by the compiler or by the libc, instead what happens is that the kernel creates a page that gets mapped into the process at startup, and we come back here to the LDD, because this is this thing, the virtual something shared object that gets mapped. It's like a, I think, 4 kilobyte page at the top. Inside it puts assembly code that is either contains interrupt 80 or contains sysenter, and then the libc, instead of making the syscall, jumps to this position and makes it such that when this thing returns, it resumes the assembly on the other side, doing some form of trampolining in this case. And by doing this full investigation, my mom's Chromebook still doesn't work, but now I know that I have this to-do here that I should implement this method. Right. So the funny thing is, so this was broken. What was the problem here? That the code, let me scroll up again. So this system call actually did not work. Why was that? Because the Chrome OS developers broke the kernel with a custom patch that was a security patch. Unfortunately, the upstream security patch was two different patches that should both be cherry-picked. They cherry-picked only one, such that if you called a syscall that did not exist, in this case, getRandom did not exist in that older Chrome OS kernel, then it would just leave all the registers unmodified instead of putting the number in that says this syscall does not exist. So that means that then systemd, doing a check for whether the syscall exists, would not see that it says eNoSys, but instead it would say it returned something. It didn't return -1, it returned 255 or what, and then the assertion would trigger. So then, of course, I also then bisected essentially the Chrome OS kernel, and I found which of the Chrome OS releases contain this problem, and of course exactly the Chrome OS release that was the release when my device was end of life was the one where this issue was newly introduced under newer Chrome OS 3.18. They actually fixed the issue by updating to a newer upstream kernel which had both things, so it's no longer a cherry pick of one of two patches but has everything in. So all of this is now very clear. Whether it is very useful is not so clear, but at least for hatrace we know that we have to implement a third possible way of making the syscall and thus deciding whether to use 32-bit or 64-bit. Going back from a little detour, okay, so we're getting very close to the end here. So you already saw a couple of implementations for certain investigations that you can make using the API. I also want to provide lots of custom tools that are useful for people commonly that you could just, let's say, download a static hatrace executable and just use it like Hstrace on your machine. So I have prepared two of them. One is the execve tree, which is often you just want to know what does a program do, what other programs does it start. You could use Hstrace filter for execve, but then you wouldn't know which PID it is unless you also filter for fork, because fork is the thing that gives something a new PID, and then execve replaces the program. So this, I want to make this super convenient, so you can say here, for example, this is just hatrace in this case, but it's on a different branch, so I just made this executable standalone, where you call bash, and you call inside true end time, which spawns another child program. There's a child program already of bash, and inside that child program I run bash again with bash -c true end and bin echo high. So if I run this, what will happen is that while the program is running and generating its output, it will print me a nicely indented tree that suggests which program is a child program of another program, and when the entire thing is over, I will collect the full tree of all programs that ever existed so that you can render it, for example, in some GUI tool or something like this. And I will just use the show instance of the map data type in here. So I run that like this, so you can see, okay, it's running bash. So then you can say, okay, this bash then is starting time, this thing here, and inside that one, a child of that is this one, and a child of that is this one, and that does echo high appears, and then at the end it gives you this Haskell data type, which I haven't bothered rendering nicely it as a tree as well. So this way, so why is this important? Because you can do it while it's running. Often when you have a program that hangs, you will never arrive down here, right? That's why it's important that you can see this here already. This might be, for example, very useful if you want to see what is GHC doing. Right? It might be calling GCC, which might call LD, which might call collect2, and this kind of stuff. And then you can exactly see what are the programs that happen inside. This is one of the tools, the execve tree. Then there's the other thing, which is for this previous problem of finding these non-atomic writes in GHC. I wrote a custom thing in Haskell, but my co-worker, Kirill, he wrote another thing, which is currently an open pull request, which is very nice. He wrote it just in this week, which is the non-atomic writes filter. And again, just adding a couple of lines essentially, you can run the following. So we can say here, if we run, I'm just going to put this there, hatrace with the special mode, and we run again our atomic write thing. So it will tell you which files did your program write to that it did not rename afterwards. So they most likely are not atomic. So that means that you can use this thing right now and run it on your programs, unmodified or closed source or whatever, right? And it will tell you which files you should probably, like where you should probably improve your code to make sure that these things are crash safe. Of course, for many files you may not care that they're crash safe. I will show that in a moment. For example, if they're temporary files anyway, right, then just like killing your machine, starting again, may just appear in a new, they may be written in a new temporary file, but this found the problem in GHC. So for example, here you can see that in a normal GHC, running this on a GHC _make invocation, it would print out these files as identified to be written in a non-atomic fashion. So for example, main.o is in there. There are also lots of other files here, which are in this case like, well, not false positives, but they are not relevant, because if you kill the machine, next time GHC runs, it will make a new temporary directory. So these not being written atomically is fine, right? For the fixed GHC, you can see this thing is absent. So if we had this program as a standalone tool before, then this investigation about what GHC is doing and why sometimes people need to clean their stack directory would have been even easier. So yeah, that is that. In this thing, we also found another thing, again by accident, which is that GHC newer than 8.6 is magically doing like 10 times less syscalls when reading archive files. So here I used Hstrace to show like, okay, how much of this like libhsghcprim.a is it reading, and we can see it's reading megabytes and megabytes of stuff again and again, while for the new GHC, it's just reading some couple bytes basically. That also means that if you, so Hstrace and hatrace and so on make programs slower, of course, because they repeatedly stop them and they have to peek all the things with one syscall per word. So you must expect a slowdown of, let's say, up to like 50x or something like this. But this slowdown was much bigger for the older version of GHC than the current master. And so it seems there must be some change in GHC very recently that makes linking insanely faster somehow, because it seems to be doing some smarter lookup in this archive file, which is really nice. I am not sure yet whether this is an actual improvement or comes from the fact that the old GHC is something that I installed from a GHC binary distribution, and this is something that I built myself, perhaps with some different options, so maybe like split objects or like split check sections is on or whatever. That is another thing that could be investigated in detail. Maybe then we find one reason why linking takes forever with Haskell, but another thing that we found on the side today. Yeah, that was the custom tools. Okay, so we're very close to being done here. So what needs doing, right? So I need your help for various tasks, which is, so it's already very useful, as I said, but I need help adding more syscalls, right? So all of these syscalls, the 250 syscalls, technically need to have enter and exit details, so it's very convenient to see what they look like, what the contents are. I would also like some technical help with reading tracey memory more efficiently. As I mentioned, right now I use the ptrace invocation to peek word by word from the other process. But there are some special Linux syscall with like read VM memory, whatever, where you can read entire buffers from other programs. That would be very useful. I need some help with generating these new features, JSON output, colored output, more specific tasks that people commonly want to do. So if you have something that you usually want to know about a problem, chances are very high that hatrace can do it. We can add that functionality as a standalone tool to hatrace so that you can add it. I need Hstrace -y, which does this pretty printing here of showing what is. So if I remove this, you can see here we write to file descriptor 3, but here it says which file that is. So we already partially have that with Kirill's newest pull request. Hstrace -c, which gives you summary statistics. How many syscalls were done and how long did they take? And we would like to check OS X support and Windows subsystem for Linux support, which is something that Neil Mitchell has asked on issue number 1. Oh no, it's doing it in this browser window. All right. Okay. Well, I should then maybe over here. So OS X provides ptrace apparently, some kind of wrapper. I don't know. Technically, I think it's a Linux specific thing, but it seems like they implemented it. I think BSD also has ptrace to some extent, and then I found on the WSL issue tracker that somebody complained about some specific option not working on WSL, which I take as the rest of ptrace works. On OS X, the problem is that the man page apparently is only very short and doesn't show these like all the details, so people complain about lack of documentation, but technically all of this could be made work on non-Linux as well, I guess, but that's something where I would like some help with. And then I have here also this longer to-do list essentially, so this is the issue about OS compatibility with some detail if you're interested, and that also a possible Zurich hack topic to implement many of those things in here. So this is the list. If you want to work on those, please file an issue so that we can track who's doing it so we don't duplicate work. But there are things from very difficult to very easy available. And then finally, like a bit of Syscall philosophy. So I think that like 95% of computer problems can be solved with Hstrace or Syscall tracing, and the remaining 4 with GDB. So this means that 99% can be solved with ptrace, right? So that's why we have hatrace here essentially. And I also think that there's this very important term of the Syscall-oriented programming, right? Forget functional programming or object-oriented programming. That's all details, right? So the only thing that matters in the end is that your program does exactly the Syscalls that it should do. If your program looks clean in Hstrace, and you can see it's opening the file, it's writing the bytes, it's closing the file, and that all looks same, the chances are very high that your program isn't actually garbage. And there are, of course, still cases where you can mess it up. Let's say you do, I don't know, quadratic sorts in the user space and so on. Those are not observable with Hstrace in this case, except from the fact that the lines between the various outputs just take longer to appear. But in general, if you get the I/O right, then that usually means that your program is pretty good. And that is a concept that we know from Haskell a lot. So why do I, as a Haskell programmer, care about this kind of stuff? Because to me, it's something that I'm already inherently familiar with, right? Because for me, this concept of user space and explicit I/O is the same thing we have in Haskell with pure function and explicit I/O in the types. For me, any program that does anything inside user space, I don't care. It's pure stuff. It cannot launch the rockets. It can't do anything nasty. And the only thing that matters is its effects. And all of its effects are system calls, essentially. So this is where like this concept of like system level stuff and Haskell level stuff, they match very nicely. Of course, there are a couple of examples where you can be tricked. So for example, if you mmap something and then write to some memory, that can reflect on your disk without you observing it as syscalls. Of course, this is by design for performance, for example. But apart from that, like almost all the other things, all the I/O is explicit and typed in the interface of the syscalls with their calling convention in the Linux kernel. And that's it with my talk, so I hope you liked it, and if there are any more questions, I'm happy to answer them, and I would like to welcome you as contributors to various syscalls, whichever your favorite system calls are. Otherwise, go through man2 and you will find some suggestions. Thanks.
So in terms of scriptable interfaces, the other thing that is reasonably popular these days is eBPF.
Yes, that can actually do
it can do more than syscalls, like can do trace perf events and whatever.
Yes,
is there a reason you built this upon ptrace rather than BPF?
Yes, so first, it's easier. Like ptrace I think is easier, and I am more familiar with it. Let me just see where the... What's this here? There's a nice diagram.
Yeah, I think it's mostly, I mean, yours is Haskell instead of Python, that's definitely an improvement. But
yeah, I mean, so there are also some other differences. The first thing is Hstrace runs without root. Right? You can run Hstrace, as I did here in the terminal, without admin capabilities. For eBPF, you currently need the sysadmin capability, so you usually need to be root. That is one reason. The second thing is I wanted to have something that's like works like Hstrace, so I can compare it more easily as well. Yeah. I think in terms of like, if you want to have something that is performant, then eBPF might be the better choice, but it's also just much newer, right? The first thing I want to have is Hstrace and Haskell, of course. There are also a couple of things that I just don't know yet how exactly they work with eBPF, because it is so new. I would have to learn a little bit about that. So for example, does it also guarantee you that you can really stop at each time to mess around with the program, right?
Yep.
How do you modify stuff? That's something that also don't know yet, have to look into that. Once we use that perhaps, then you get more capabilities though, because this, as you can see here, Syscall is only one of the possible things that eBPF can hook into, and you can do all kinds of other stuff with it as well. So I find it very interesting, and that is also a topic that I actually discussed today with Kirill, how we can do that. But I think we might first want to have full Syscall capability and then do this. But yeah, I find that very interesting, and I find it good that Linux actually gets better and better in terms of tracing. And yeah, as you could see, there are still some open problems in terms of like actually knowing what is going on and having to like peek into the memory and so on. Yes. Anything else? Doesn't look like it. Then I'm ready for the pizza.
Thank you very much, Niklas.
Thank you.